And I realized I should do an example in here. So I will do that example, and then we'll talk about your homework. All right? Let me begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to guide our work today, Lord. In your name I pray. Amen. So I couldn't find the error for the midpoint rule yesterday, and I don't know. I was looking. I had Thomas's calculus with me. For some reason, I couldn't find it in there. So I stated the error bound for the trapezoid rule and also for Simpson's rule yesterday, but this is the error for the midpoint rule, right? So let's look at a specific problem, and I'll try to make the function a little bit, in some sense, a little bit maybe easier to analyze than the one I did last time. But let's try to answer the following question. Right? What n is needed for the error in the midpoint rule to be less than 0.01 for calculating the following integral. Integral from, let's say, 0 to 1 of e to the minus x squared dx. So if I want to calculate the integral from 0 to 1 of e to the minus x squared dx to within 0.01 of the correct result, to be sure, how many steps in the midpoint rule do I have to, how many midpoints do I need to use? How fine a partition do I have to pick in order to make this happen? All right. Now here, this k, what is k? It's the same as I think I stated m yesterday. What's this k? It's a bound for what? What is k a bound for? So here, we're assuming that k is f prime prime. I believe f prime prime of x, the absolute value of that, is less than or equal to k for a less than or equal to x less than or equal to b. All right. So we have to find a bound on the second derivative in order to put this estimate into action. Okay, so let's do that. Let's actually let's use the error estimate and figure out what the k should be, and then from that we'll figure out what n should be. All right? So here f of x is e to the minus x squared, right? So I want to talk about, really the thing I'm most interested in is explaining to you how to bound the second derivative here. Okay? So what's f prime of x? Looks like we've got a minus 2x e to the minus x squared, yeah? What's f prime prime of x? What's that? 4x squared minus 2 times e to the minus x squared, yeah? So what you said was one of the terms, but it's a product rule, right? So I also have to do a product rule. And the product rule brings out that minus 2, as well as the initial 4x squared, which comes from minus 2x quantity squared. So this is by the product rule. Okay. And then, all right, how about the third derivative? And why would we care about the third derivative? What would the third derivative tell us? It would tell us where the second derivative was increasing and decreasing, right? So if I had the third derivative, I could easily ascertain the minimum and maximum values for the second derivative function over the interval of 0, 1. So let's calculate the third derivative. It's going to give me 8x minus 2x times 4x squared minus 2 e to the minus x squared. what I did was I differentiated the 4x squared minus 2. That gave me 8x. And that multiplies e to the minus x squared. Then plus 4x squared minus 2 times the derivative of e to the minus x squared, which is, of course, is the minus 2x and the e to the minus x squared. But we can factor the e to the minus x squared out. All right, what do we got here? Let's clean it up. F prime 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 of x equal to, what do we got here? 8x cubed. We got 8x cubed. Looks like plus 4x plus 8x, yeah? Did I miss anything? Oh, that's a minus 8x cubed. That probably should take that into account. Is that? So we could simplify that further, right? The third derivative is, what is it? I can factor an x out, right? So it's x times 12 minus x squared, is it not? Well, not x squared, but there's an 8 squared. 12 minus 8x squared. 8 squared. Right? Hey, that we could factor further, right? So we find f prime 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 of x is x times, let's see here, the square root of 12 minus x times the square root of 8 times the square root of 12 plus x times the square root of 8. So I'm looking at this as the difference of squares, right? This is a squared minus b squared, and I'm identifying a is equal to the square root of 12, and I'm identifying b is equal to x times the square root of 8, right? But difference of squares factors into a plus b times a minus b, which gives me square root of 12 minus x root 8, square root of 12 plus x root 8. Okay, great. Thus, zeros of f prime 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 of x, in other words, looking for this equal to 0, are at where? X equals to 0, right? And also x equal to what? Square root of 12 over the square root of 8, right? Oh, that's the square root of 12 over 8. What is that? Three halves? Square root of 3 halves, whatever that is. And also where? So long story short, what is the square root of 3 halves? I don't really care, but what is it? It is definitely where? Not in 0 to 1, right? So these two guys are outside. 0 less than or equal to x less than or equal to 1. And this is at an endpoint, right? So to maximize slash, minimize, whatever, to find max min f prime prime of x, we need only consider what? Right? Endpoints, right? So what's f prime prime of 0? What's f prime prime of 1? These are the winners and losers in the max min game for the second derivative over the interval of 0 to 1, because there are no critical points, because the third derivative is non-zero, right? And so what do you got? Zero minus 2 times e to the 0, right? I'm using the second derivative. And then the other one is 4 minus 2 times e to the minus 1. So we've got a minus 2 for f prime prime of 0, and we've got a 2 over e for f prime prime of 1. And you put this together, you've got minus 2 is less than or equal to f prime prime of x is less than or equal to 2 over e. For 0 less than or equal to x less than or equal to 1. Yeah.
Why are we using 0?
Because what we're considering is the integral from 0 to 1. So we want to analyze, we want to find a bound. Our goal at the moment is to find a bound for the second derivative. We're trying to bound f prime prime of x on 0 less than or equal to x less than or equal to 1. That's the motivation of all this calculation I'm doing at the moment.
So were we looking for something in the third derivative?
The reason we're looking at the third derivative is if we want to find max mins for the second derivative, right? If there was a critical point, then we should think about that because it could be like the maximum in the interior between 0 and 1. So really, we're using the closed interval test on the second derivative function. Yeah.
What do you mean bounding it?
That means this. We're trying to find a number which is larger than the second derivative, the absolute value of the second derivative between 0 and 1. So, look at this here, right? This says that the second derivative is as the smallest possible is minus 2. The largest it can be in positive value is 2 over e. It's about 2/3. Yeah. We're trying to find the k. We're trying to find a k which bounds the second derivative.
Yeah, and all those values between the -2 and 2 over e could be k.
No. The question is, what is k? We're trying to figure out what k could be. We need this. We need that the absolute value of f prime prime of x is bounded by k. Now, this inequality is equivalent to saying minus k is less than f prime prime of x is less than k. If you have the absolute value is bounded above by k, that means it's between plus or minus k. So you tell me, what should I make k given the calculation that we've done? We've established this inequality right here. What should I make k equal to? Yeah, I should make it equal to 2. Because certainly this is less than 2, right? So I can put a minus 2 here, I can put a 2 here, that's true. And I don't think I think that's about as good as I can do. So we find f prime prime of x is less than or equal to 2 for 0 less than or equal to x less than or equal to 1 and f of x equal e to the minus x squared, all right? Is this calculus 2? Yes, it is calculus 2, but what I'm using right now is really calculus 1, right? This is graphing with calculus applied to the second derivative. Now, so now we can answer that. We can. Yep. Yep.
So how can you use the bound made with the zeros of f triple prime of x? You said f triple prime of x is equal to 0. You got square root of 3 over 2, negative square root of 3 over 2.
Uh-huh.
How did you determine 0 and 1 from that?
Well, that shows that the critical points of the third derivative are 0 and plus or minus square root of 3 over 2. But plus or minus the square root of 3 over 2 are not in the interval 0 to 1. So if I'm trying to find optimal values for the second derivative, I look for critical numbers in the third derivative, and that's right. So we just have to, closed interval test says look at critical points and the endpoints, whatever are actually relevant on the closed interval of consideration, which here is 0 and 1.
So those points are inside that 0 and 1 interval.
These are?
No, they aren't.
Okay, they're not. I missed the nit of you. That's okay. There's no telling what I'll do on a given day. If those had been 2/3 instead of 3/2, then it would all have been different, right? Okay, so what have we got? So now we face choose n such that what? The problem we're facing now finally is our k is 2, our b is what? A equals to 0. So we want 2 times 1 minus 0 cubed divided by what? Divided by 24 n squared. We want this to be less than or equal to 0.01. Yep.
Just choose your bounds for 0 and 1.
Yeah, that was in the given problem. Because we're trying to integrate from 0 to 1. So that's what fixes the a and the b. So if you're trying to solve this inequality, I think the easiest thing to do is just to solve the equality and kind of go from there. Right? So like this is really just saying 2, I mean, good grief, this marker is worthless. Ah. All right, so let's get to it. So this gives me 2 is equal to 0.01 times 24n squared in the case of equality, which tells me n squared is equal to what? 2 divided by 24 times 0.01. Right, so n is square root. I mean, this is not going to work out to be a specific natural number. We're going to have to use some common sense here and go from whatever we find, right? Let's see what we get. I think I got the square root of 8.33. Did you guys get that? I don't know. Now I got to take the square root of that thing. So I get 2.88. Now, is n equal to 2.88? No. So use n equals to 3.
Now, why is that? Because you can't use a decimal? Or
Yeah, what would the 2.88 midpoint rule mean? Like, what's 2.88 steps? Now, so let me just draw a picture. So here's the function we're looking at, e to the minus x squared, is the bell curve. All right, so here's 0, here's 1/3, here's 2/3, here's 1. What are the midpoints? 1/6. What's the second midpoint? What's halfway between 1/3 and 2/3? Is it a half? Oh, okay. What's wrong with me? What's the third midpoint? 5/6. All right, so if you believe this, we're saying that picking the midpoint, we can approximate the integral of e to the minus x squared using just three midpoint rule to within 0.01. This is actually relatively easy to calculate. What's m3 equal to? F of 1/6 plus f of 1/2 plus f of 5/6. What's the delta x here? It's 1/3, right? So we have e to the minus 1/6 x, e to the minus 1/6 squared plus e to the minus 1/2 squared plus e to the minus 5/6 squared times 1/3. That should be within 0.01 of this integral. Can you guys see it? Come on. Uh-oh. Got to be careful not to pull these wires too long. If you do, you'll pull stuff over inside, but it's locked, so you can't fix it. Not that I've done it before. Uh-oh. Well, I hope you got that. Now, personally, if I'm going to do a calculation like this, I would tend to use something like Wolfram Alpha just so I can see what I'm doing. You might say that kind of defeats the purpose because, after all, you could just do it numerically and Wolfram Alpha just the same, right? But remember, the point here is not actually the answer, it's the process. So we have exponential of, what is it? Minus 1 divided by 36, yeah? Plus the exponential of what? Minus 1 divided by 4. Plus the exponential of what? Minus 25 divided by 36, yeah? Which is 2.25. So I take all of that. I divide by 3, right? Oh, Wolfram Alpha, aren't you cute? Your exact expression. Oh, there we go. Allegedly 0.750. All right, we'll do. What's the actual integral of the? Oh, by the way. Oh, look, 17. 17? 17? That's it, though. All right. I was waiting for 17. Oh, 18. All right, now. It's very exciting. I'm going to stop. Stupid top hat. Integral. I said it, I know. Oh, man. Don't worry. Integral of e to the minus x squared from x equal to 0 to x equals to 1. It's 1/2 square root of pi of 1. What do you know? 0.746. As you can see, what's the error? So the actual integral, if you trust Wolfram Alpha, is 0. What is it? 746. So what's the actual error here in M3? It's about what? 0.004, right? Which indeed is less than 0.01 as we desired. Error, yeah. So the math works, yeah? Yep. Well, the theorem about bounding the error, it involves, you have to bound the second derivative for the midpoint rule error. Be glad I didn't ask about the error in Simpson's rule. That involves bounding the fourth derivative. Yeah. Anyway, enough about that. So, the rest of the time I will either work applied problems or take your questions about homework. So, open the floor for homework questions at the moment. Problem, what was it? 37. Ah. That I'll take yours next. Let's see here. So problem 37. A picture of it is roughly this. You have a sphere, right? And the radius r has a cylindrical hole of, so this is r. And then you're drilling a hole of radius a out of that, right? So after that hole is done being drilled, I'll draw a two-dimensional picture of what's going on here. So the hole would be something like this. So here's A, and here's R. And let's see here. So basically, you've cut off the top. You're chopping off like the top sliver of the sphere, right? Because as you drill through, you're flattening out essentially. You're cutting a hole, a cylindrical hole through the middle of the sphere is what the problem's asking about, right? Cylindrical hole of radius a less than r drilled through its center. Find the volume of the resulting solid. So if I could foolishly attempt another picture at this thing, we're trying to calculate the volume of something that, roughly speaking, looks like this. Oh, I can't ever draw this thing worth anything. I fail. So you're trying to calculate the volume of something like this. Do my pictures make sense of it? So how should you calculate such a volume? What method would you use? Shells or washers, right? You could go either way here. This problem could be solved with shells or washers. Which do you guys want to think about? Washers? Right, if I do think about washers, then you'd be looking at something like, here's a typical washer, right? So if I draw that again down here on its lonesome, what's the inner radius versus what's the outer radius? So the inner radius is fixed, right? Any washer that you take, its inner radius is governed by the inside drilling hole, right? So Rn is just equal to A. But R out, well, that's a variable, right? So in this picture over here, this is what that washer would look like. All right. So we're trying to figure out what is, I mean, this in the picture would be R out, right? I mean, if we think about this point as being x comma y, we could do that. If we do that, what's the thickness of the washer? I heard a dy. That makes sense to me because it's a y thickness. And with that setup, what's the outer radius? X minus a, nope. Not dx, nope. I mean, what is this distance? called relative to that point? It's just x. So what's the volume of this little washer? Right, it's pi r out squared minus pi r in squared. Why? Because that gives you the area of the annulus, right? That gives you this area. That's what this is, the area of the annulus. And then to get the volume of the infinitesimal washer, we just multiply by the thickness, which in this case is dy. Right? And that would be pi times what? Pi times x squared minus, I guess, a squared, right? dy. What does dy tell you? It tells you that you need to do an integration over y. What should y range over? Negative r to r would make sense if it was the whole sphere, but it's not. All right, there's a max y up here. There's a minimum y down here, right? And y is stuck between those. By symmetry, I think we could double the integral from 0 to y max and get the volume, right? So like the volume should be twice the integral from 0 to y max of pi times x squared minus a squared dy. But what is y max? You got to take ownership of the middle picture, right? You think it through for yourself.
Would it be the height of the cylinder that you got divided by 2?
No. Let me draw a triangle. If you look right here, this leg of the triangle I just drew, the length of that is y max. The hypotenuse of the triangle has length r because it goes to a point on the sphere. And so that's the line which connects the center of the sphere to a point on the sphere. The other leg to the triangle has length a. I heard something. Square root of what? R squared minus a squared. We have a winner. Yes. Can you do that integral? Should you do that integral? There's unfinished business in the integrand, isn't there? Is x a fixed constant here? No, x varies with y, does it not? So what should we do? We should try to rewrite that x in terms of y, because we have to have expressions in terms of y in order to do the integration. How are x and y related? There's yet another triangle we could draw, like this one, right? That would, in my other picture has this right here. I just didn't want to draw it in the other picture. There's already enough going on there. So what do we have? X squared plus y squared equal to? Right. So what's x squared is equal to? R squared minus y squared. Now that is an honest-to-goodness function of y. And so you see what we have is 2 times the integral from 0 to the square root of r squared minus a squared of pi times r squared minus a squared minus y squared dy. And that's why this could be asked in Calculus 1, because this is an integral that you can do in Calculus 1, right? Now, you guys picked washers. If it had been up to me, I'd have picked shells. And if you pick shells, I think you end up with something you need to do like a trig substitution on, if I remember right. Question? Let's go through the setup of shells for this problem. So in this problem, if you look at so here I'm drawing the sort of this kind of picture again. A cylindrical shell would look like what? It would look something like this, right? I have a hard time drawing it three-dimensionally, but over here, that would look something like this. All right, and so if I drew it over here separately, this would be the cylindrical shell. The thickness of the cylindrical shell would be dx, right? What's the radius? Well, the radius here is just x. What's the volume of a cylindrical shell? You take 2 pi x, all right, and then times the height. And then the thickness is dx. So what's the height in this case? So I heard y. I don't quite agree with that. Y, the height is not just y, it's what? It's 2y, right? And what was y equal to? I just erased it. Yeah. So you guys told me x squared plus y squared equals 2 r squared. So that y I can rewrite as 2 pi x, the square root of r squared minus x squared dx. And that would be for what? A less than or equal to x less than or equal to what? I mean, you have a cylindrical shell starting with radius a and going all the way out till r. Radius r. Now, radius r, it's kind of hard to see. Like the cylindrical shell out here gets awful tiny, right? But yeah. And so in that case, you have to integrate that, Again, I guess it's still a calculus 1 integral. I'm sorry, I've assigned you a Calculus 1 problem. What's wrong with me? I should have found something that comes out to uglier integration. Yes?
You said it was 2y, right?
Yeah.
So why did you?
Oh, I lost my 2. I said it, but I didn't do it. So there's a 4 there. Thank you. All right, enough about this. You had a question about 17? Oh, 17, let us remember that
That's my integration.
so, as we discussed a while ago, we can write sine and cosine in terms of imaginary exponentials, but more to the point, you can derive identities from that, and one of the ones that you could derive is the product of cosines is like so, all right? But there's also a product of sines formula we can derive, namely that sine of ax times the sine of bx is 1/2 cosine of here it is. I'll put it down lower. You know, so if you have p here and you have q here, and p and q are not equal, then you just get, you know, p plus qx and p minus qx. Those can both be integrated with a u substitution for problem 17. When you do that, the bounds are minus pi to pi. So after you use this identity, in the case p not equal to q, what you should get is like sine of n pi for all of the either upper or lower bounds when you evaluate. But the thing is, sine of any integer multiple of pi is 0. So the answer to this problem should be 0 when p is not equal to q. On the other hand, when p is equal to q, something else happens, right? When p is not equal to q, you can use this identity to do the integral, and after you go through that, you should get 0. The answer. So what I'm saying is when you have p and q here and they're not equal, because we can trade this product of sines for that integral, the sum of cosines, both of those cosines integrate to sine. When you plug in minus pi and pi to that, you'll get 0. You have to work it out, all right? So I'm giving you a hint. Now, if p and q are equal, what is this? Yeah, I heard sine squared. So we have sine squared px, and we can do that a different way, right? I mean, I guess you could still use the formula. I mean, if you put p and q equal, what does this give you? 2px here, and p minus p, which is 0, so you get 1/2 of cosine 2px minus 1. Oh, it's sine squared, yeah, minus 1. I am suspicious of this formula. I think this formula is off by a minus 1. When I plug in a, and if I plug in a equals to b, right, I should recover sine squared as 1/2 of 1 minus cosine 2ab. 2ax, and I'm not doing that. This is off by -1. That's supposed to be minus. This is supposed to be plus. So this won't change your work if you've already gone through it, right? I think the next one's okay. If I put a and b equal, I recover the 2 sine theta cosine theta equals sine 2 theta identity. So as a check. Anyway, I need to fix that. Now, if you didn't follow my notes and you just derived it from the imaginary exponentials like I tried to show you guys, then you wouldn't have gotten in trouble. But even so, again, this integral works out to 0, so plus or minus 0, same answer. This, on the other hand, does not integrate to 0, does it? What's this integrate to? I'm not, all right, this is a hint. That's as far as I'm going. Next question. If I say more, I've solved the problem. So, yeah. Do number 4, please. I'd rather not. 4 is a challenge problem, and so to actually work this out, it'll take us the rest of class. But I can kind of give you a sense of what's going on here. There are many possible answers. So if we put p at -2, 1, and we put q at 4, 4, so roughly over here, guesstimating, then the question is, where can R be in order to form a triangle where the interior angle of R is 60 degrees? So like, for example, here-ish is 1. But there's also like another answer down here somewhere. Potential R there, right? But if you start looking at this, you can see that there's another one up here, over here, or over here, or over there, or down there somewhere. There's infinitely many answers to where R could be. So what I would do is I would do, like I said in the problem, put A, B there, and work out conditions on A and B which ensure that the interior angle at R is 60 degrees. And geometrically, you can see that if you wanted to be lazy, you could do something like, I don't know, assume R is on the y-axis, right? Because there's going to be an answer there that could be found by sliding R up and down like that. So without loss of hope for an answer, we could make R equal to, I don't know, 0b. And then it just becomes a problem of finding which b will make it work. But then, to answer the question, you have to do the trigonometry on the triangle, either using vectors or falling back to right triangle trigonometry. That's your business. But
so do we have to find like all points for R to be, or just
no.
one?
I will be happy with just one. But a more draconian reading of my problem would say find all possible R. It's a little bit, the way the question's worded, you could kind of worry it's that, but that's not my intention because I don't want to grade that. So just find a solution, I'll be happy with it, right? That is, of course, a question you could ask, like describe all possible choices of R which make that 60 degrees. There's a whole infinity of them. Yeah. Yeah. I can try. Aha! Thank you. Fantastic question. Integral of x over x squared plus 1 squared. I take your problem and replace it with the integral of dx over x minus 1 times x squared plus 4 squared. Haha. Okay, so this is worse, but very much related. You said 24, right? Yeah, okay. I changed the problem. So actually, this inadvertently is almost the same as problem 26, isn't it? Anyway, problem 24 and problem 26 are very much in the same vein. They're both partial fractions, and so we're facing something like 1 over x minus 1, x squared plus 4 squared, and the question is, what's the partial fractions decomposition for such a thing? The answer is this. A over x minus 1 plus bx plus c over x squared plus 4 plus dx plus e over x squared plus 4 squared. All right? And now let's work it out. So we have 1 is equal to a times x squared plus 4 quantity squared plus bx plus c times x minus 1 times x squared plus 4 plus dx plus e times x minus 1. And we need to figure out what a, b, c, and d are. Any, yeah. So one very nice thing to do is to just put x equal to 1. Putting x equal to 1 is a very nice thing because then we just get 1 is equal to a times 25. These other two things are 0 when we plug in 1, right? So therefore, a is 1/25. Then what's next? What's that? -4. I don't think -4 helps us, though, because then nothing, I mean, -4 doesn't really kill anything here. Yeah.
Set the coefficients, well, after you multiply out the two other terms,
Very, yeah. Right, we can multiply out and equate coefficients. Another good way to do it. But in the spirit of showing you something new, we could plug in the 0 of x squared plus 4. What's that? What's that? 2 doesn't work. 2i. 2 times the square root of minus 1. You're like, are you allowed to do that? Yes. Yes, you are. If you do that, you get 1 equal to, what happens when you plug 2i into these? 0, 0, not 0. So it gives us 2id plus e times 2i minus 1. Now, what the gentleman in the back row said would be the completely logical, straightforward thing to do on the basis of what I've already done in class. But I would be negligent not to share this secret with you. You can plug in the complex root. It's sometimes very, very helpful. This is such an example. Now, but it's better than just that. Yes, it makes everything go away, but we have to multiply this out. What's I squared equal to? Yeah, -1, so I get minus 2d minus 2id, I'm just distributing, plus 2ie minus e. Let me rewrite that. So what we have is minus 2d minus e plus I times minus 2d plus 2e. That is all equal to 1. So if you look at equation star, this is a complex equation. Yep. Oh, have I done that? 4i. Oh, yes, yes, thank you, thank you. Indeed. And that's, part of my larger point here is things work like you expect them to. So you can still correct my mistakes. Woohoo! All right. That's good? But check this out. Usually when we plug in a 0, we get what? We get like one equation. Plugging in a complex 0 gives you not one equation, but two equations. One for the complex, one for the imaginary part, one for the real part. I get, from this single star equation, I can read real part equals to real part. That gives me 1 is equal to minus 2d minus e from the real part of the equation above. From the imaginary part of the equation above, I get 0 is equal to minus 4d plus 2e. Now it's two equations, two unknowns. We can destroy that, yeah.
Shouldn't that negative 2b also be a negative?
Oh, I think I put the 4 in the wrong place. That was, oh, I'm sorry. You guys made a correction, and I took your correction, made it into a new mistake. Let me fix it. So this is supposed to be minus 2id. That's this times that. That's what that is, okay? This was supposed to be the 4i squared, which is minus 4. All right, sorry. Now, that puts a, thank you about that. Thank you for that. Minus 4 there. I'm putting the corrections in red, and the minus 2 here, right? If you multiply the second equation by 2, we get 2 is equal to minus 8d minus 2e. And then the other one was 0 equals to minus 2d plus 2e. If you add those equations, this gives us 2 is equal to minus 10d. Therefore, d is what? Looks to me like d is minus 1/5. Yes, sir?
How did you get 0 is equal to negative 2d plus 2 imaginary?
So on the left-hand side of the equation, we have 1 plus I times 0. I can equate the real part to the real part. I can equate the imaginary part to the imaginary part. And those give me this equation and that equation, respective. Two complex numbers are equal only if both their real and imaginary parts match up. A single complex equation is a pair of real equations, most often. But anyway, any way you slice this problem, it is a difficult problem. It's got five parameters you got to figure out, right? So this will help you a little bit. Now, after you're done with that, are you okay on the integration of these things? So this is like u equals x minus 1. This is a denominator substitution and also an arctangent. And this one, we can, for the x term, we can make a w equals x squared plus 4 substitution. For the e term, again, we can use a x equals 2 tangent theta substitution there like we did the other day. But anyway, I think mostly you should know what to do. Once I write what's in blue down, it's just a matter of like turning the crank and working through the algebra. Do you know how to check your answer? There is a simple method, and I do allow it. But I mean, don't use this to do your homework, but it's good to use it to check your homework. So we were just working on, what was it?